Space and Science News. With James. In the realm of cosmic mysteries, few phenomena capture the imagination quite like supermassive black holes. These gravitational titans lurk at the centers of galaxies, wielding power that can reshape entire cosmic landscapes. For decades, scientists have been tantalizingly close to understanding their true nature, but critical pieces of the puzzle remain just out of reach. The Event Horizon Telescope represents a quantum leap in our ability to probe these astronomical enigmas. By combining radio telescopes across the globe, researchers have achieved what was once considered impossible, imaging the very edges of black holes and unraveling their most closely guarded secrets. Today, we'll be talking about the Event Horizon Telescope's groundbreaking work on black holes and their jets, because why not? The story of how humanity is pushing the boundaries of scientific exploration is more compelling than any fiction. What drives these cosmic monsters to launch jets spanning thousands of light years? How do magnetic fields near a black hole's event horizon create such extraordinary phenomena? And what revelations might fundamentally transform our understanding of the universe? Some discoveries are so profound they challenge everything we thought we knew about space, time, and the fundamental mechanics of our cosmos. The next few minutes will take you to the razor's edge of scientific discovery. Let's dive deep into this subject of black hole imaging and cosmic jet formation. The Event Horizon Telescope, EHT, has already made history with its groundbreaking images of black holes, reshaping our understanding of these mysterious cosmic giants. Now, this same technology is positioned to provide answers to one of the most compelling questions in astrophysics: how do supermassive black holes launch powerful jets of high-energy particles into space, reaching speeds close to the speed of light? This new research effort, led by Anne-Kathrin Baczko from Chalmers University of Technology in Sweden, aims to push the boundaries of what we know about black holes even further. The EHT's ability to capture detailed images of black holes relies on a global network of radio telescopes working together to create an interconnected system capable of producing extraordinarily high-resolution images. This technique, called Very Long Baseline Interferometry, VLBI, has already allowed scientists to peer into the hearts of black holes, and now, it's being used to reveal new, thrilling details about the supermassive black hole in the galaxy NGC 1052. By combining data from multiple radio telescopes across the globe, the EHT team is not only able to capture an image of the black hole but also gain unprecedented insights into the magnetic fields at its edge, which play a crucial role in the formation of jets. The galaxy NGC 1052, located 60 million light-years away from Earth, has been a focus of intense study for this very reason. This galaxy hosts a supermassive black hole at its center, one that emits powerful jets of high-energy particles into space. These jets are some of the most energetic phenomena in the universe, extending far beyond the confines of the host galaxy. Understanding how these jets form and why they can accelerate particles to nearly light speed is one of the biggest challenges in modern astrophysics. Scientists know that these jets are linked to the magnetic fields near the black hole, but the precise mechanisms remain unclear. How does the black hole generate such immense energy? How are particles in the jet accelerated to speeds that defy comprehension? The research team's work represents a giant leap toward answering these questions. By taking intricate measurements of the black hole's environment, Baczko and her colleagues have been able to map out the structure of the magnetic fields that surround the black hole. These fields are believed to be responsible for channeling the energy that drives the jets. Through this innovative research, scientists are beginning to piece together the puzzle of jet formation, unraveling the complex interplay of gravity, magnetism, and particle acceleration that governs these awe-inspiring phenomena. In the coming years, the EHT will continue to refine its ability to capture even more detailed images of the black hole and its jets. As the team's work progresses, it could lead to a deeper understanding of not only how jets are launched but also how they shape the environments of entire galaxies. By exploring the magnetic fields, the energetic jets, and the region surrounding the black hole, scientists are venturing closer to unlocking the fundamental processes that drive some of the universe's most dynamic and mysterious events. This breakthrough could be a game-changer in astrophysics, offering new insights into the power and reach of supermassive black holes. NGC 1052 stands out as a particularly unique and challenging target for the Event Horizon Telescope, EHT, offering both great promise and substantial difficulty for astronomers. Anne-Kathrin Baczko, the lead astronomer from Onsala Space Observatory at Chalmers University of Technology, describes it as one of the most complex sources the EHT has tackled, even more so than previous black hole targets. The galaxy, located some 60 million light-years from Earth, is home to a supermassive black hole that generates two incredibly powerful jets, which stretch across thousands of light-years into space. These jets are among the most energetic phenomena observed in the universe, and they are the focus of the EHT team's investigation. The team's research goal goes far beyond simply imaging the black hole at the center of NGC 1052. Their ambition is to uncover the very origins of the galaxy's east-west jets, which are launched from the supermassive black hole at nearly the speed of light. To capture this elusive and dynamic phenomenon, they needed to devise a strategic approach, one that could provide a clear picture of the complex mechanisms at work. Unlike some other observations made by the EHT, which utilized the full array of telescopes in its network, this particular study was conducted with a more focused configuration, using just 5 telescopes. Each telescope was carefully chosen to optimize the observations, giving the team the best possible chance to gauge the black hole's behavior and its jets. The inclusion of the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile proved crucial to the success of these observations. ALMA's exceptional sensitivity allowed the team to capture the faint emissions coming from the supermassive black hole and its jets, something that would have been nearly impossible with less sensitive instruments. To supplement this critical data, the team also relied on observations from other telescopes, further enhancing the richness of the data they gathered. The faint and largely unexplored nature of the target made these observations inherently uncertain, adding an extra layer of difficulty to the task at hand. The complexities of observing a black hole and its jets from such a vast distance, especially when the emissions are weak and hard to detect, posed a significant challenge. However, the strategic use of ALMA's sensitivity combined with the data from the other telescopes proved to be highly effective, allowing the research team to gather valuable insights into NGC 1052's black hole and the jets that emanate from it. These observations, though just a stepping stone in a much larger research effort, mark a significant achievement, one that brings us closer to understanding the behavior and origins of these powerful cosmic jets. The research team's recent efforts have provided 2 crucial pieces of information that inspire confidence in the potential for successful imaging of the supermassive black hole in NGC 1052. These findings mark significant progress toward unraveling the mysteries of black holes and their powerful jets. The first major discovery is that the region surrounding the black hole emits a bright glow at a specific frequency of radio waves, perfectly tuned for detection by the Event Horizon Telescope, EHT. This glow, known as synchrotron radiation, ensures that the black hole and its environment will be visible to the array of telescopes, laying the groundwork for future observations and imaging. This breakthrough is vital, as it guarantees that the team will be able to observe the black hole clearly, allowing for more detailed study of the jets and the forces at play near the event horizon. The second important finding involves the size of the region where the jets form. The scientists determined that this area is comparable in size to the ring around M87, the first ever black hole to be imaged by the EHT. This measurement suggests that the jets of NGC 1052, much like those from M87, are large enough to be captured in full by the EHT array. This revelation is crucial because it means the telescopes will have the capacity to resolve the black hole and its jets with sufficient detail, providing the team with the opportunity to study the dynamics of jet formation and the surrounding magnetic environment. Beyond these promising imaging prospects, the research team's measurements have also shed light on the magnetic conditions near the black hole. The strength of the magnetic field close to the event horizon was estimated to be around 2.6 Tesla, roughly 40,000 times stronger than Earth's magnetic field. This finding aligns with previous estimates for NGC 1052 and has significant implications for understanding how the black hole operates. According to Matthias Kadler, an astronomer at the University of Würzburg and a team member, this powerful magnetic field could play a pivotal role in the black hole's behavior by preventing material from falling directly into the black hole. Instead, the magnetic field may redirect the material, enabling it to power the formation of the galaxy's 2 massive jets. These discoveries provide essential new insights into the mechanisms behind black hole jets, bringing scientists one step closer to understanding how these incredible phenomena are formed and maintained. The future of black hole imaging is set to undergo a transformative shift, thanks to upcoming advancements in radio astronomy. 2 major projects on the horizon, the Next Generation Very Large Array, ING-VLA, from the National Radio Astronomy Observatory and the Next Generation Event Horizon Telescope, ING-EHT, are poised to push the limits of what's possible in black hole observation. These next-generation telescope networks promise to offer unparalleled sensitivity, broader wavelength coverage, and enhanced resolution, enabling scientists to explore black holes in more detail than ever before. As radio astronomers prepare to utilize these advanced systems, the insights gained from recent measurements of NGC 1052 have provided valuable guidance on what to expect from future imaging efforts. One key finding is that the center of NGC 1052 shines particularly bright at wavelengths around 1 mm. This specific wavelength is ideal for creating the sharpest possible images with current technology, making NGC 1052 a perfect candidate for detailed study by next-generation telescopes. However, the discovery doesn't stop there. The team also observed that the spectrum of NGC 1052 becomes even brighter at slightly longer wavelengths, further enhancing its appeal as a prime target for these future telescopes. This increased brightness across a wide range of wavelengths means that the upcoming telescope networks will be able to capture high-resolution images and data that reveal unprecedented details about the supermassive black hole at the galaxy's center. The implications of these findings are immense. As ING-VLA and ING-EHT come online, they will enable scientists to observe black holes with a level of clarity and precision previously thought to be unattainable. The combination of greater sensitivity, broader wavelength coverage, and improved resolution will provide astronomers with the tools to investigate not just the black holes themselves, but also the powerful jets they launch and the extreme environments that surround them. These upcoming advancements in technology may finally allow researchers to unravel the mysteries of how supermassive black holes accelerate particles to nearly the speed of light and how they sustain these immense jets over vast distances. The future of black hole imaging is brighter than ever, and the coming years promise to bring groundbreaking revelations about some of the most enigmatic objects in the universe. The groundbreaking research on NGC 1052's black hole, published on December 17, 2024, in the prestigious scientific journal Astronomy and Astrophysics, marks a monumental step in black hole studies. The paper, titled The Putative Center in NGC 1052, was led by Anne-Kathrin Baczko from Chalmers University of Technology, with an impressive team of 286 co-authors. This vast collaboration highlights the scale and complexity of the project, drawing together expertise from numerous institutions around the globe. Key contributors from Chalmers included John Conway and Michael Lindqvist from Onsala Space Observatory, as well as Chiara Seccabello, who has since moved on to AI Sweden. The breadth of this collaboration underscores the collective effort needed to study such a challenging and distant target. The success of this research would not have been possible without a global network of telescopes that provided the necessary observations. The study relied heavily on the Event Horizon Telescope (EHT) network, which brought together 5 key telescopes: ALMA in Chile, the IRAM 30-meter telescope in Spain, the James Clerk Maxwell telescope, and the Submillimeter Array in Hawaii, as well as the South Pole Telescope in Antarctica. These telescopes worked in unison, capturing data that formed the backbone of the findings. In addition to these crucial instruments, the team also incorporated data from 14 additional radio telescopes within the Global Millimeter VLBI Array, GMVA. This network spans several countries, including Spain, Finland, Germany, and the United States, with notable contributions from the 20-meter telescope at Onsala Space Observatory in Sweden and the telescopes of the Very Long Baseline Array, VLBA, in the US. The EHT collaboration itself represents the pinnacle of international scientific cooperation. More than 400 researchers from Africa, Asia, Europe, North and South America contributed to the study, working together toward a common goal: to capture the most detailed black hole images ever obtained. By linking telescopes across the globe, they created a virtual Earth-sized telescope capable of peering into the heart of the black hole in NGC 1052. This unprecedented collaboration and technological feat are pushing the boundaries of our understanding of black holes, their jets, and the extreme environments that surround them. The ongoing efforts of this global team promise to reveal even more astonishing insights into the nature of these enigmatic cosmic giants. The Event Horizon Telescope represents more than just a technological marvel; it's a testament to human curiosity and our relentless pursuit of understanding the universe. What began as a seemingly impossible dream has transformed into a global scientific collaboration that is rewriting our comprehension of cosmic phenomena. By connecting radio telescopes across continents and synchronizing data with unprecedented precision, scientists have achieved something extraordinary. They've peered into regions of space once considered completely unknowable, revealing the complex mechanisms behind black hole jet formations and magnetic field interactions that shape entire galaxies. The research on NGC 1052 is just the beginning. Each observation brings us closer to understanding the fundamental processes that drive cosmic evolution. These magnetic monsters at the center of galaxies are not just passive objects, but dynamic engines of creation and destruction, launching particle streams that can extend thousands of light years. Future generations of telescopes like the ING-VLA and ING-EHT will continue to push these boundaries, offering even more detailed insights into the most extreme environments in our universe. The collaboration of over 400 researchers from around the globe demonstrates the power of international scientific cooperation. If you found this exploration of black holes fascinating, hit that subscribe button. Drop a comment below about what cosmic mystery you'd like us to explore next. Your support helps us continue bringing cutting-edge scientific discoveries directly to you. A special thanks to all the researchers, astronomers, and scientists who continue to expand the frontiers of human knowledge. Until next time, keep looking up and staying curious. Thanks for watching. Remember to like, subscribe, comment, share and click that notification bell so you never miss out. See you next week.